So my next speaker, I would like to welcome. Well, first of all, we'll move to a new topic now. So we are going to talk about software and deep learning. And my next speaker is Leo. Leo comes from Munich, from the company Elunic. And Leo is going to talk about use AI to an automatic inline 100% visual inspection for complex component. So Leo, the floor is yours.
Thank you. Thank you. I hope you can hear me. My name is Leo, and I'm a data scientist. I'm going to tell you, maybe give you a bit insights on how deep learning is automating hard to automate inspection processes. So first of all, to give you some background about the company I'm working at, we are a full solution provider. We do machine learning, we have some software, and we do the integration part from a hardware perspective, plus from a system integration perspective. So we see a lot of customers struggling in every step of the process, and we try to help them. Normally, when we enter a production site, this is how it looks like. Even today, even in the 21st century, a lot of people sitting there looking at the products. In this case, actually, there are a lot of women, and women are better quality inspectors because they have a longer attention span. So men get, for example, yes, men get paid less in that job because they do a worse job. But anyway, I think in a time where everything is digital and everything is automized, such I would say very boring tasks should get automated as well. And now with deep learning, we have the technology to actually do that. So why is it still checked manually? I mean, there's a lot of machine vision already. It has been there the past 40 years. So why there's still so many human labor human labor in Germany, but also in other European countries is very expensive. So why there's no solution yet to the problem? And maybe we can do a test, and you can have a look at that image. It's a solar cell, and maybe you can try to find the defect. I give you some time. And maybe for those who are already using computer vision systems, think about how to implement a solution to find the defect once you found it. So I give you a small hint. There's a defect. Maybe let's go for some, I would say, common computer vision feature used like threshold calculation. So let's put the threshold up and see if we can find a defect again. And maybe you can agree with me that there's a defect, but also there's another one which maybe looks the same. There's another one, there's another one. So there are some limitations to the current state of how computer vision works. And now imagine engineering a solution for that problem. And I guess it will be very costly. So you will spend a lot of time again, and that is one part why it's not automated yet, because it's just easier to put some human there doing all the work than putting engineering power into that. Second part might be accuracy. In that case, I don't know how accurate you can tune a system that is capable of detecting all those images, the defects. And in the end, once maybe you have this very costly algorithm, let's say it has some okay-ish accuracy, and then something changes in the production. Actually, those are old images. Now solar cell production went to half of the size, so maybe all your algorithms don't work anymore, and you can start all over again. So how can artificial intelligence automate all that stuff? And maybe, I guess you're all educated and you all heard of it, but I want to go through the process just for the protocol, how deep learning works. And now that is a neural network used in computer vision, or actually the deep learning part of computer vision. And those are already there, have been there many years. And that's a basic problem of cat and dog classification. You give in an image, and you get out the label of cat and dog. The next thing, you can give in some text, and in the end, it plays a song. Maybe you all have some Alexa Siri at home telling it to start a song. And newer, I would say, achievements in the field is you give in a text, and it puts out an image. So there's a lot of movement in the whole field. And the technology went further and further from just classifying cats and dogs to now doing actual problem solving in production sites. So maybe let's go back to the problem that we had. There's our defect. And maybe you all know that training neural networks is based on image data. So images of good images, like the cat and dog problem, and images of bad parts. So here, to train an algorithm to teach it how to detect such defects, we need to tell the algorithm somehow. And we cannot just tell him, like, that's a defect. But we need to show that somehow to the algorithm. So we mark those parts that are defective in the image. And then we start the training. So we take good images, we take bad images, we take the labels, and we get some accuracy. Now, most of the time, the first model is not the best model. So you start somewhere, you train it, and it comes out. And now comes the nice thing about deep learning. Maybe we already have this low accuracy, and if we do it with computer vision, now we need to do more engineering, more how to fix this problem, maybe some other threshold, maybe some other method to solve the problem. And in the case of deep learning, you just use more data. So we put in more images, we give more image data to the algorithm, and it gets better. But we all know if a production site is producing defective parts all the time, it would not be in the market anymore. So no one has images of defective parts, and if so, there are very little. And since if we don't want to start a project and finish it in 10 years from now, we need to have some other methods to have some equally balanced class, which are OK images and defective images. So for that, I want to tell you one trick, which is augmenting the training data. So for example, here's another defect. And now, for us, it would look the same. But for the algorithm, if we flip it horizontally, that's a completely new information to the algorithm. So with just one image, if we flip it, we can make two images. And we can keep doing that, flipping it vertically, horizontally. We can also distort the perspective, which is also, again, a new information. Maybe for us it's clear that this one is the same as that one, but for the algorithm, that is completely new information. So we can keep doing that. We do brightness adjustments. We do some contrast. We can blur it. We can whatever. And in the end, the most important thing is that we keep the labels. So whatever we do, we need to keep the labels. And now with only one images, I can show you an example. We have the original image. We can flip it. We can rotate it. We do some 5 different perspectives of it. And we do some different brightness. And we combine all those things. We can do that automatically. That doesn't cost us anything. And in the end, we have, out of 1 defective images, we have 1,800 defective images. So that is one solution to the big problem that deep learning faces, and which is now possible to solve with such techniques. Then another thing is using pre-trained models. So we all know that training a neural network is it needs a lot of data. So even now, if we now start training a model, it would take days and millions of images to get to a point where it understands what is a shape, what is round, what is circular. That is all. It needs a lot of data to understand that. So first, we randomize the weights of the model, but we don't do that. Already, big companies like Google, Facebook, all of them, they already train some very big networks, and we can just use them for our purpose. Thank you, open source. Then we take those images, and we apply, let's say, COCO pre-training. That means we take another model and fine-tune that model for another task. So for example, in our case, we take some defective images. So before it was random, then it got some sense of how the world looks like, and now we take defective images and go to the next thing, where we go for a specific domain. So for example, I've been talking to a guy who's doing a street inspection. So before it was maybe just a crack in general, and now we go for cracks on streets and do fine-tuning on that task. And with every step we go deeper into the field of pre-trained models, we need less data for the next step of training. So here you see, first one, for example, MS COCO has 330,000 images. Then we only use 7,500 images of defects, and then even less, let's say, 1,000 images of solar crack defects. That is the second trick I want to give you, how to get better with deep learning and solve the problem faster. And the last thing I want to share with you is very interesting to me, and it's synthetic data. So you don't need the defect to be there, but you can just create it yourself. And actually, Google did it, not Google, Microsoft did it for the HoloLens. It's used like you can use it by moving your hands. And you can imagine they take an image of your hands, and it can be anywhere. So whatever, it can be here, it can be at home, it can be at a production site. So it needs to be very robust to the environment. And they cannot take an image of every environment everywhere. So they just started creating those synthetic hands and moving them somewhere with different backgrounds. So here you have, you can change the light setting. You even have a depth camera, which is very good for 3D, for example. And you have perfect synthetic labels. So since we create those images in a computer, we know where the object is that we placed. And in the end, we know where the labels are. So we have perfect labels, and we don't have to work anymore. The computers do. So that's also a good way to tackle the problem. So now my question is deep learning a game changer? I'll let you answer the question, but I can tell you, once you implemented the system, it's much cheaper. So if you want to continue training, if you want to make it better, if you want to adjust the algorithm, once you have the pipeline, it's much cheaper to get to a better accuracy, for example, because you don't need more engineering power, but you just need more data. And data is kind of free, for example. It's electricity. So that is one part. The accuracy goes up over time. So the longer you use the system, the better it gets. It's not like you use it one day and then if it's bad, it stays bad. But you introduce the system, and then over time it gets better. The last part is flexibility. I try to combine it with costs, but in the end, if you have a system that is running, if you have an inspection system that is running, and you change your production, let's say you move from a black part to a yellow part, or you change the shape, you can use the same system, you can use the same pipeline to train the model for a different purpose, and so it's very flexible. There are even today a lot of I would say practical applications of machine learning, for example, in casting production, PCBs I saw here as well, in pharma and automotive a lot. So different industries use the technology on a different, I would say, for different purposes, but in the end, it's every time it's deep learning and it's defect detection. And before there have been a person doing the inspection task, and now there are algorithms assisting them and making their job easier. So that was it. I want to invite you checking your components with our software. You can get a demo code here, and I'm open for questions. Or maybe
questions.
or maybe not.
So usually people, yeah, let's give you a hand. Leo, well done.
Thank you.
Thank you. So, is there a question? Feel free to raise up your voice or to use the chat.
Normally, there's always one.
Yeah, here. Oyvind has a question.
Ah,
yes.
I have a question, yeah. So how long does it typically take to, in this example that you went through with the solar panels, how long did it take from like idea to actually pushing this out and actually running inspection on it?
That's a good question because it depends on when you see the project as finished. So you can go very quickly to the first version of the model, but maybe the customer is not satisfied. Maybe you're not satisfied because you say, okay, I cannot trust the system enough. I need to train it a bit more. So from the first idea to the implementation, you can go in like let's say 2 days. Because you annotate your images and you train the model, which takes maybe less than 10 hours, and you can deploy it. You can use it from there, but I would not suggest that because the accuracy will be, as showed, not so good in the beginning. So that can be very fast. But if you want to have a good model, that takes more time. So we go for a approach that is. It should not distract the worker in his or her work to do the inspection job. But doing that, we still want to have the labels like the decision. That is a good part. That's a bad part. And we try to make a good process around that, so the project can take how long ever it wants, because the inspection person is not hindered in its job. So, yeah.
Great. Fantastic.
Thank you.
Thank you.